Hi, I'm Anirudh. I'm a software engineer at Rockset. Prior to this, I spent a couple of years at Google working on Kubernetes and big data and machine learning on containers. I'm also a Spark committer.
I'm Schter. I'm the CTO and co-founder of Pepperdata. We do total performance management solutions for big data systems.
Cool. So what we have today for you is the agenda is a little bit of an introduction as to what this project is all about. I'll go into what Kubernetes is and maybe introduce a few basic concepts that you'll need to understand the rest of the presentation. Sean will do a deep dive into the technical aspects of Spark on Kubernetes and demo as well. And beyond that, we'll talk about what is planned work for Spark 2.4 and onward. So Kubernetes and Apache Spark, the same time last year when I was giving this talk, we were a fork, a completely separate fork, and before that we were in a whole bunch of other repos as well. Today we are part of the released Apache Spark 2.3. It's an experimental feature, but if you were to download Spark 2.3, you should just be able to play around with Kubernetes. We've had contributors from a whole bunch of different organizations over a year, and yeah, as of today, it's actually running in production in a bunch of places. So a little bit of background. What is Kubernetes? And this is the most succinct definition. It's from the website. So the key thing to remember here is it is open source, and it's used for management of containerized applications at scale. So that's what Kubernetes is. Show of hands, how many people here have used Kubernetes? OK, that's a significant number. How many use it in production? OK, awesome. So for the uninitiated, this is more of why you might think about Kubernetes. It has a whole bunch of features that make it enterprise ready, and I'll explain what I mean by that. It's features that fit in well with a large enterprise when you have many different teams, many different personas within your organization that are all doing different things with a shared cluster. So for example, there's namespaces and quotas. This is a Kubernetes feature that lets you, say, give a different logical view of your cluster to different teams. For example, you have a data science team and a web server team. You want them each to have different views of the cluster so their applications don't interfere with each other. And at the same time, you want to impose constraints. You want to be like, maybe the data science team only gets to use X gigs of RAM and so many CPUs, right? Similarly, there's access control, which is super important. You want to be able to say who has access to what kind of resource and what they can do with it. So it's features like this, and of course, a lot of these features are pluggable, like the authentication and authorization mechanisms. The ones that you use in your enterprise could be made to work with Kubernetes because these mechanisms are pluggable. And there's a whole host of logging and monitoring tools out there as well that are open source and can be used right out of the box. The other cool thing about Kubernetes is how versatile it is. And if you just look at this diagram I have on the right, it's like a whole bunch of serving applications already used to run on it. This is Nginx and Apache Web Server and so on. Increasingly, we see people trying to run workloads which have like a stateful component to it, like MySQL and Postgres and Elasticsearch. And this talk is about Spark, so Spark and Jupyter and TensorFlow as well. And of course, there's higher level workflow orchestration tools like Airflow, et cetera, that also work on Kubernetes. So the overall picture here is that you can run all of these workloads on a single cluster, and that not just improves the utilization of that cluster, but also lets you get away with smaller staff that is managing your cluster, because you don't necessarily have to have one siloed cluster for each kind of application. This is more of the technical details of Kubernetes, so you get a little bit of an understanding as Sean goes into detail later. So everything, at its core, the smallest schedulable unit is a pod. A pod can contain one or more containers. So if you look at the diagram on the top, you see a pod with 1, 2, and 3 containers each. The pods schedule onto nodes. Nodes might be physical or virtual machines. Each node runs a node agent called a kubelet. For people familiar with Yarn, a kubelet is like the node manager. All communication with your cluster is going to happen through an API server. So you would say, you would talk to the API server, say, create a pod or something else. But as you can see, pods are probably are pretty granular in that they're too fine-grained for you to manage a large application. So what Kubernetes gives you is controllers. So controllers are, you can think of them as a glorified control loop. So all it's doing is talking to the API, finding the current state of whatever resources you want to control, comparing it with the desired state that you've expressed to it, and reconciling it constantly. So if you look at a replica set, for example, is a built-in controller in Kubernetes. So I've just told the Kubernetes API, give me a replica set that that's running Nginx, and give me 4 replicas of that. So in that case, that controller is running within Kubernetes and constantly reconciling with the API server to ensure that I have 4 replicas running at all time. So even this isn't complex enough for you to run all kinds of applications, right? So running 4 copies of something is much simpler than what Spark does, for example. So here's where custom controllers come in. Because Kubernetes APIs are accessible to all of us, there's no reason why those core controllers are special. So you could write your own controller that controls pods, secrets, configuration, et cetera, have your own custom setup and teardown logic, and have it driven by your own API. So in some sense, Spark is pretty much this. So if you look at the definition on the right, we're specifying the number of executors, et cetera, and an image for it to run. And the Spark application itself is acting as a controller and reconciling and going back and forth with the API server to ensure that your Spark application is running correctly within Kubernetes. Yeah, and now I'll hand off to Sean for the technical deep dive into Spark.
Thank you. Very nice. Yeah, so I'm going to talk a little more about how Spark on Kubernetes works. First, I'm just going to make sure that I define exactly what terms I'm using in terms of Spark. So at its core, Spark has 2 main parts. It has the driver here, which orchestrates everything that's happening on the cluster, and it has a set of executors. Right? And the executors check in with the driver and say, hey, are there any tasks you'd like me to do? Is there any data you'd like me to cache? And just keeps repeating that. So this is the main architecture that we're going to talk about how it works within Kubernetes. So first, the core work that was done to make Spark work on Kubernetes was to make the Spark driver a custom controller in the exact same sense that Anirudh just talked about. So the driver is acting as the controller for Kubernetes, doing things, API requests to Kubernetes on behalf of the work that needs to get done. And then these executors are all containers that run inside of pods on Kubernetes. And you can see that for each different application, it's got its own controller and its own executors. Now, if we look a little more under the hood, what's happening here? There's the Spark core, which is the main Spark core code, which is mostly agnostic to where it's running. And that Spark core has things like, here's how I want things to be configured, and I want so many executors now, or I don't need so many executors now. So that's the responsibility of the Spark core. And in the case when it's running on Kubernetes, it hands the control, the calls to actually affect those actions into this new code that was written called the Kubernetes scheduler backend, which runs in the same, inside the driver and speaks Kubernetes interfaces. And so if you look on the right here, you can see in each little circle here is representing a different container that is also in a different pod. The red one is the driver. And then the driver requests to Kubernetes, hey, I'd like some executors that are going to run in this container. And Kubernetes then starts up the blue things, the executors, which do their regular job of tasks and caching on behalf of the driver asking them to do that. For people who are used to running Spark, how you'd call this is going to look pretty familiar. So this is an example of Spark submit. But of course, you could also use the Java or Scala API to create Spark contexts. You can run notebooks. I'm actually going to show an example of this. And coming soon, you can use a Spark shell. So if you look at the example here of the Spark submit command line, I've highlighted the 2 things that are different, right? The white stuff should be super familiar. The master here You specify a master, but instead of specifying a master like yarn or something like that, you're going to specify k8s and the location of the Kubernetes master. And that basically puts the internals of Spark into Kubernetes mode to use the Kubernetes scheduler executor. The last thing is this configuration to say, hey, what is your image? What is your Docker image? What is your container image that you're going to use for launching your driver and your executors? And this is, of course, critical in the case of Kubernetes. You have to know what container you're going to launch. And so this is, and there's a registry that Kubernetes is configured to use, and so it pulls it out of that. So there's a big, I want to take this opportunity to mention why the container, running your application in containers like this, running your executors in containers is super useful. So mainly it's because it encapsulates all of your different configuration and dependencies. In fact, the entire file system image that your driver and your executors are going to see is completely encapsulated in this Docker, right, in the container. And so that has a huge advantage because you get a completely consistent environment for how your executors and your drivers are going to run, whether they run on your laptop or on a test cluster or on your production cluster. As long as they're running the same container, right, and you can Docker push these all around, you're going to get the exact same environment. Therefore, you're going to, if you feed it the same input data, you're going to get the same results. And this is, as compared to, systems that say you might use a library that exists in the OS file system somewhere on your, on your cluster, right? This is a common thing that might happen on a yarn cluster. And you have to make sure that the libraries that your execution environment is going to pick up are exactly the same version as what you might have on your laptop or on that other cluster over there. If you're not, you can get hard to understand bugs. And Anirudh is going to talk a little bit about some of the benefits of Kubernetes before I show a demo.
Yep. So this is building further on the custom controller pattern that we were talking about. The Kubernetes API, the way it is structured, lets you build controllers that act on other controllers. And I'll detail in a minute what that helps us do. So when you declare a new API that can itself have a control loop that creates other controllers, other complex applications, you can create higher level concepts for yourself. So an example here, to put it concretely, is the Spark on K8s operator, which is worked on at Google and is Apache 2. So what that gives you is a declarative implementation of the Spark submit semantics. So you could, for example, the specification on the right shows you how you would declaratively specify a Spark job, and the Kubernetes API and a controller are then responsible for doing the Spark submit operation on your behalf. And to take that a step forward, you could have automation to, say, schedule a Spark job, cron-like functionality where you want it to run periodically once every 2 hours or n hours, right? So, and the Meta controller project is another good example of this. It lets you build these, small control loops that you can then use to orchestrate at a higher level these Spark applications themselves. So this is kind of the core. The fact that you can have these composed layers lets you build higher and higher level automation. Yeah, off to the demo.
Yeah, so the demo I'm going to show is it's an example of why there's some benefit of having Spark. Oh, my volume? Is that better? All right. So the demo I'm going to show is an example of why there's a significant benefit of Kubernetes for this kind of workload. So we're both going to be running Spark on Kubernetes. Of course, that's the main point of the talk. But Kubernetes, as we said earlier, is very versatile. So it allows you to run other things. So in this case, I'm going to run a notebook. I'm going to run a Zeppelin notebook, right, inside Kubernetes as well, right, submitting Spark apps to the same Kubernetes cluster. So you don't need a separate place to manage your long-running service, this Zeppelin notebook, as you need to run your Spark application. So I pre-recorded this, although this actually all ran on this computer, just for speed. So first we're going to use Minikube, which is a way to run a single node Kubernetes cluster on, say, a laptop or a server. You can download this from the web. So I start up this little VM, and at various points in this demo, it actually takes about a minute to start, but I sped up the video. So Minicube's going to start up, and the other thing we're going to do is we're going to tell Docker to use the registry that's built into this Minikube for building images. So we're going to build some images here. So that's what that eval is about. So then the next thing we're going to do is we're actually going to build a Docker for Spark. Now one could get this publicly, but I wanted to show soup to nuts here. So this is, we're actually going to get Apache Spark mainline code. So you can see, this is the actual mainline, pull. This was as of last night. So then the first thing we're going to do after we get a pull is we're going to make a Spark distribution tarball, right? And this takes, many minutes. And so this is an example of the video going much faster. Once we get this Spark distribution tarball, the next thing we're going to do is we're going to unpack it. We're going to CD in there, and we're going to use a script that's designed to build a Docker image. In this case, it's actually building the image right in the Minikube Docker repo. You could, so there's not going to be any pushes of the Docker image around because it's built right in the repo. Next thing we're going to do is we're going to build Zeppelin. Zeppelin is actually published as a Docker, but unfortunately we can't use that because it's not it has a it's not compatible with the mainline of Spark yet. It will be soon. But fortunately, the master branch of Zeppelin is compatible. First, we select that we're going to use Scala 2.11. Next, we're going to build the Zeppelin source fully. And then the last thing we're going to do is we're going to build the Zeppelin Docker. I had to do one little tiny patch here because the Zeppelin Docker build process really wants to download an official Zeppelin package from the web and not use your local one. So I patched the Docker file to use the locally built one. And that's the only patch to the source that was done in this whole demo. Right? So you can see, we're going to post this later, so you can, you can see the whole patch that was done. So now we do a Docker build, and this was massively sped up. The first time you do this, this might take quite a while because it has to, pull a whole bunch of things from the web. But once that's done building, then the next thing we're going to do is we're actually going to start the pods. So first we're going to look at the local Kubernetes cluster, and I'm going to, we're going to look at the images. Those first two images are the images that we just built. We're going to see that there's no pods running, and the only service is Kubernetes itself. Now Kubernetes, you specify configuration for your services and pods with YAML files. So here is the file for the Zeppelin pod. In particular, it has this app label of Zeppelin UI. We're going to refer to that again. So we use kubectl to create this pod. This will actually tell its definition to the Minikube Kubernetes cluster, and then the Kubernetes cluster will start it running. Second thing is we need a service to create a DNS entry. So we allow the executors to find the driver by name. Notice there's that selector of app Zeppelin UI. That means it's referring to that pod. We create the service. So now we've got that Zeppelin pod running, and we've got a Zeppelin service for DNS purposes. So next thing we're going to do is we're going to configure Zeppelin and actually start running some notebook. First thing is, in order to make it all accessible to my laptop, I'm going to use a few kubectl proxy lets me access the Kubernetes UI, port forwards to access the Zeppelin UI and the Spark UI. So here's the Kubernetes UI. We can see the only thing that's running is our Zeppelin pod. Now here's the Zeppelin UI, so I'm connecting into that pod right now. First we have to configure the interpreter. The Spark interpreter is all the way at the bottom, so we scroll down to that. The main thing we have to do first is configure the master, so that we're going to use that k8s:// which tells us to be in Kubernetes mode, and the master address we're going to use is the address to the Kubernetes cluster that we're actually running in. So I paste that in here. The next thing we're going to do is we're just going to tell this Spark interpreter to use 2 executors. This is standard Spark configuration. The next thing we have to do, of course, after that is we're going to have to say what image we're going to use. And so the image we're going to use is the Spark image that we just built, right? And that's its name and its tag. And then there's a couple other options that we have to set. We have to allow this, say what the driver pod name is, so the executors can find the driver. And the last thing we have to do is we have to say, hey, this is going to be running inside the cluster in client mode, and we have to disable Zeppelin's version check. It has a version check to say, hey, is the version one of the versions we support? Since I'm building off the trunk, it doesn't know about my snapshot version number. So now we're actually going to go to my Pi estimator notebook. Very, very trivial program. We have to tell it that the Spark interpreter is bound to this notebook. And now I'm going to click the little Go button right next to finish there. And that will actually start the Spark interpreter running. We'll see that there. If we go to the Kubernetes UI and we refresh it, first thing we'll notice after it refreshes is that there's a couple executors that have started up. So they're waiting to start. Next thing we're going to do is we're going to take a look at the Spark UI. In the Spark UI here, we can see that this job is here. It's just starting its tasks, 8 tasks, 11 tasks done. If we go back to the notebook, the Zeppelin notebook provides us this nice little progress bar that's watching all those tasks complete. So we can see that it's busy estimating my pi. And once it finishes that, we'll go back to the Spark UI. We can see, we'll see that all the tasks are done in the Spark Web UI. Refresh it, and we'll actually see that it's 1,000 tasks done. And then the last thing we'll do is we'll go back to the Kubernetes UI, and we can see the Spark executors are, the Zeppelin pod is running, and so are my Spark executors that the Zeppelin pod started. I didn't start those, this custom controller did, right, and did it on my behalf. And of course, they'll keep running, in the case that I run some new thing in my notebook and they're sitting there ready to run. You might want to reclaim those, but that's an upcoming feature that I'm actually going to have, that Anirudh is going to talk about next. So, Anirudh?
Yeah. So that was a demo of what's possible today. Now we're going to talk about upcoming features and things we're currently working on and excited about for the next version. First up is PySpark. This comes from popular demand. Pretty much everyone's asking about it. So this is the ability to submit PySpark jobs to a Kubernetes cluster, which in turn, if you were to have PySpark and then have a Jupyter pod in a way similar to what Sean just showed, you could have Jupyter connecting to that and running your Python Spark jobs as well. So this includes like argument handling and specialized Docker images. These Docker images are going to contain all of the Python dependencies in them, so you could just get started and run your PySpark jobs. It also features a couple of improvements to the way memory is handled, the overhead factor, especially for non-JVM jobs. So this is nearly done and on its way in, I think waiting for integration tests or something like that. Another exciting feature is dynamic allocation. So this one is a little more complex. So dynamic allocation is this feature that lets Spark request a certain number of executors, and during the course of the execution of an application, it can make more requests, or if there are no tasks for a particular executor to run, it could spin them down. So that way, your your application kind of becomes elastic during the course of its lifetime. So the complexity here appears from when executors are these entities that could come up and go down, you want to persist the shuffle files that are being written because you might need them for a later stage. And those shuffle files are managed by an external shuffle service that currently, as of right now, expects to share disk with the executor. So to solve this particular problem, we've come up with a couple of different approaches. So for one thing that's being worked on in its very early stages is to remove this shared disk dependency between the external shuffle service and the executor pods. Alternately, and this is what we did prior to this, it is to have Kubernetes kind of provide a certain mechanism so that, so these would be local persistent volumes and host path, for those familiar with Kubernetes, in order to share disk, which is on the node between two pods, which are, one of them is the executor and the other is the external shuffle service. And this is the overall roadmap. So as of 2.3, as you saw, cluster mode works fine. There's container build tooling, which is all of those scripts that you saw that Sean just ran, which lets you build the container. And then there's Java and Scala support. All of the libraries that are built on top, like Sparse SQL, those work out of the box anyway. So for 2.4, we're planning PySpark, super important. Dynamic allocation and solving that problem. Notebooks, this is sort of works now, but you saw that there was some special config that it required. So this item is more for making that workflow a little more accessible and easier. High availability, this one's important, especially when you have long-running streaming jobs and you lose your driver and you want it to come back up and resume state, like resume from checkpoint. So that's something we're working on. And official container images, because no one wants to build an image every single time. So having official images as your base would certainly speed up that workflow, and Spark R. And then beyond that, there's also work for local file staging, which is more like, how do I get files that are on my laptop onto the cluster in a more seamless fashion? There's queues priority, preemption, gang scheduling, et cetera, some of which need work on the Kubernetes side as well, and that's ongoing, and cluster autoscaling. Finally, it's open source. There's a Jira component for Kubernetes, so we'd love to have you try it out and then tell us what you think. Come back with feedback, PRs, everything is accepted. There's the mailing lists. The last item here is the Kubernetes special interest group for big data. So that's a little broader in that it deals with Spark as well as other things in the ecosystem like Airflow and HDFS. So we have weekly discussions and a Slack channel if you want to get involved in any of those projects as well. That's all. Questions?
There are microphones in the middle of each aisle if you'd like to ask questions. We have about 3 minutes.
I was curious about your driver HA comment for Spark 2.4. Do you have maybe a reference we might be able to track down that Jira from?
It was hard to understand, but you said, are there Jiras for the Spark 2.4 features?
Yeah, the Spark 2.4 driver HA feature in particular that you mentioned.
Sorry, you said?
For Spark streaming, you mentioned that there was work for driver HA.
Oh.
HA
sure.
driver?
Yeah.
I think there's, I don't know if this is on. There is an issue tracking it, but I don't know that work has been done in that regard. There was a proposal with regard to this to use a Kubernetes job object, which is like a higher level controller that can manage the lifetime of the driver pod. But there are some details to be worked out.
Yeah.
I have a question about the latency of getting the containers. So if I want to scale my job, right?
Yeah.
I have 10 workers, and then now maybe there's a stage that needs 200 thing, and then it's going to pull that. So what's the latency of getting those containers up in Spark on Kubernetes, and how would it compare to something like Spark on Yarn?
So it's going to be extremely similar to what you've seen on Spark on Yarn. At Pepperdata, we've got both Kubernetes clusters and Yarn clusters, and they're extremely similar because Docker's launched so fast. On my Minikube on my laptop, it's a little slower because I'm running out of RAM, but on a real cluster, it's fractions of seconds to get a new thing up.
I mean, so if I'm running a workflow that's it's got a few stages, let's say 50 stages, and in the middle, it can give and take executors and still come back in a couple of seconds.
Once we do the dynamic allocation work, yes.
Okay.
Yeah.
One additional point there is there's also, you pay the cost of pulling the image exactly once per node. So it's cached on the node. So if another executor were to show up on that same node, you wouldn't pay the cost of pulling that image because it's pre-cached on there.
Yeah, so I'm doing that thing manually right now, but is there also a way for it to know that, hey, this guy already has in the local node Docker, it has already pulled an image, let me schedule something here rather than in a new node where it's going to take 3 minutes to pull the image?
The Docker does this for us.
Yep.
No, but you have to know which node to schedule it on, right?
No. There's one central repo for the whole Kubernetes cluster, and then the individual nodes pull that image to their node, and that's completely automatic.
No, but if you already know that this node has the image pulled and that one doesn't, then you probably want to schedule it there.
Yeah.
That's a huge hit otherwise.
It could be, but I think if you're commonly using the same base Spark image for lots of Spark apps, it gets cached everywhere pretty fast.
Yeah.
Hi, I'm on your right.
Work in this. So if one of the executor dies,
Sorry.
and do you do it with Kubernetes replicas, or that is that, and you bring a completely new instance?
So
or how
the
does
question
that-
is, if an executor dies in the middle of a run, what takes care of making sure that there's a new executor?
So the driver, as we were talking about it, is a controller in some sense, right? So it's constantly looking at the Kubernetes API, getting the current state, and reconciling it with the desired state. So in this case, the desired state is expressed at the number of executors that it wants. So yes, the driver is responsible for that.
And, yeah.
So will it invoke
give-
a new pod, or there will be a replica
Let's give
for
a-
the pod which was there previously, which will be replaced?
In this case, we don't actually use a replica controller, I think, for the executors. We have the driver itself is doing it.
So it will invoke a new pod, driver will
The driver will create a new one.
Okay, cool. Thank you.
All right. Anybody with questions, come. Yeah.